Hi physics class, I want to make a video about charges entering mutually perpendicular electric and magnetic fields. So check this out. What we're going to find is the acceleration of electrons entering these fields. So let's digest this a little bit. We got parallel plates, so there's going to be a uniform electric field between them. You've got the potential difference and the separation, so we can get the electric field. Within the plates, there's also a magnetic field. Okay, the X's mean going into the page. Okay, so it's like above the page there's the North Pole, under the page there's the South Pole, so the magnetic field lines are going in. So what's going to happen is a charge coming in is going to experience an electric force from the field, from the electric field, a magnetic force, because there's a magnetic field, and moving charges produce a magnetic field, we know that. So there's going to be two forces, we'll have to figure out their directions, get a net force, and from there get an acceleration. And just because I can, I also added the fact that these are accelerated through 120 volts, so there's an extra step here to find out their speed. Okay, but it's certainly all within our skill level. So let's go through it. Before we can find the magnetic force on this charge, let's find its speed. So just remember, anytime you see a voltage, especially this word, charges being accelerated through a voltage, that's just going to tell you how much kinetic energy they gained. Okay, so these are electrons multiplied by that 120 volts, and you'll get how much kinetic energy they have as they come out. Okay, the reason we're doing this is to get speed, so we'll just use our kinetic energy formula. Okay, and done this a few times. Double the energy, divide by mass, take the square root. Okay, I get 6.49 times 10 to the 6 meters per second. Okay, so that's how much speed the electrons enter this region with. Okay, so once they're in here, there's going to be an electric force, which will just be QE. Okay, that's how to calculate it. Let's talk about the direction though. Electrons are negative. Okay, I find some students, once we learn magnetic fields, forget what they know about electric fields. There is no hand rule for electric fields. It's just a negative is attracted to the positive. Please don't think any harder than that. So the electric force is going to be directed up toward the positive plate. All right, the magnetic force, which is QVB, well, this is where we need our hand rule. Okay, so electron means we gotta use our left hand, thumb to the right, fingers into the page. I don't know how well this will show up. Oh, terribly. Okay, oh, here I come. So something like this. Okay, so my thumb's to the right, fingers into the page, my palm is facing down. So that tells us that the magnetic force is going to be down. Okay, so electrons coming in here, electric force will pull it up, magnetic force will push it down. So when we calculate these two, to get a net force, we'll actually just end up subtracting them. Okay, so let's calculate these. The electric field between plates, as we know, is just delta V over delta D. So that's going to be 9 volts divided by 0.06 meters. Let's see what we get here. Okay, so these electrons are being pulled up by 2.4 times 10 to the negative 17. Let's find the force pulling them down now. Okay, we use our voltage from over here, or sorry, our speed from over here. Okay, I'm gonna get creative here with my paper. The magnetic field is 40 microteslas, so that's going to be 40 times 10 to the negative 6. Okay. When I punch that in, (4.16 times 10 to the negative 17 newtons, and that was down. Remember, we got that from a hand rule. Okay, so these electrons, as they're coming in, electric force up, magnetic force down. The net force, well, we'll just combine them. I'm going to look, the magnetic force is greater, so I'm going to say it's 4.16, oops, subtract the electric force, and it's going to be down, right? It's down minus, well, down plus and up, but it's down minus down. Our answers here are going to be up. Excuse me, our answer here is going to be down. So our net force is and just a reminder there, since I made a mess out of my language, the magnetic force down is greater than the electric force up, so our net force will be down. Okay? And remind me, what are we looking for? We're looking for acceleration. Well, that's easy. We got the net force. We're pretty much done. So let me put it near the middle of the page so it stands out. Okay, we're just going to invoke Newton's second law here. Our acceleration will be the net force divided by the mass. Okay, I've seen a couple of you guys over the years, people like to put the charge back in instead of the mass, and that's not a good idea. So just let me finish this calculation here, and we'll be done. Okay, so that electron's going to get sucked down pretty fast with a high rate of acceleration, which is interesting because it'll collide into the negative plate, which it doesn't want to do, but that magnetic force is overcoming the electric force. All right, hope this helps. Good luck out there.